In this experiment, bomb calorimetry was used to determine the caloric content of two types of non-nutritive sweeteners, one containing aspartame and the other containing sucralose. This experiment required three major tasks. The first was calculation of the heat capacity for the bomb calorimeter itself. This was accomplished by combusting benzoic acid and recording the temperatures of the water surrounding the bomb at 30-second intervals. This was performed 3 times. The next task was to calculate the combustion enthalpies for both sweeteners. This required combustion of each sweetener product in the calorimeter and recording the surrounding temperature of the water at 30-second intervals, just like with the benzoic acid runs. Each sweetener was combusted 3 times. Benzoic acid was simultaneously combusted during these runs to promote complete combustion of the artificial sweeteners. The third task involved calculating the caloric content of the artificial sweetener products, as well as the pure aspartame and sucralose compounds. The Food and Drug Administration data on the metabolism of aspartame and sucralose were used to determine their caloric values. This picture shows the setup for the bomb calorimeter. Here you can see the pail. This is a par bomb calorimeter. We have a pail here inside, another pail of water, and the bomb inside of there. I have my thermometer recording the temperature, and this stir back here, which is circulating the water for more even temperature measurements. Because this experiment involves combustion under pressurized oxygen, several safety precautions were taken. I wore safety goggles, gloves, and lab coat all times during this experiment. I triple-checked all the valves and seals on the bomb. I stood back for 30 seconds after first igniting the bomb, and according to the par bomb manufacturer manual, I used no more than 25 atmospheres of oxygen, this is the oxygen tank here, to avoid compromising the bomb seals. In this experiment, the bomb calorimeter is treated like a closed system, and combustion was considered adiabatic and isochoric for all runs. The combustion enthalpies were calculated using this first equation right here. To obtain the change in energy values, delta E, it was necessary to first calculate the heat capacity, this minus C of S, for the calorimeter using data from the benzoic acid runs. The adiabatic temperature changes, this delta T equation right here, was determined by plotting the temperature versus time for each of the runs. Also, it was necessary to correct for the combustion of nitrogen in aspartame by titrating the bomb washings with 0.0709 molar sodium carbonate solution using methyl red indicator. Here you can see a picture of the bomb calorimeter I used. The pail of water. This is the bomb itself. These are the leads that cause combustion inside the bomb, and this is the pressure release valve for the oxygen. So after collecting my data and plotting the data and taking into account energy corrections, I was able to determine the mean caloric values of the sweeteners. These are the caloric values for the serving sizes of the sweeteners, and the mean caloric values for each of the artificial sweetener compounds. So you can see aspartame sweetener has a higher mean caloric value at 3.80 compared to the sucralose sweetener, 3.31. Similarly, pure aspartame has a much higher mean caloric value than does pure sucralose. I used t-test analysis to compare the two sweeteners, and the difference between them is significant at the p is less than 0.05 level. I also used t-test analysis to compare these two values, and the difference between them again is significant at the p is less than 0.05 level. This column right here lists the margin of errors for the mean caloric values. These error margins give the range over which the sample caloric content can deviate at a confidence level of 95%. So here we have graphical representations of the results from the previous slide. Starting with the first graph here on the left, we can get a visual for how significant the difference between the caloric values for pure aspartame and pure sucralose really is. The error margins are indicated by the error bars here and here, and these are quite small. Now compare that with the caloric values for the serving sizes of the whole sweetener products. Each product contains mostly dextrose and maltodextrin, and just a small percentage of the aspartame and sucralose compounds. These are actually 4% aspartame and 1.2% sucralose in each packet of sweetener product, as indicated by the manufacturers. The dextrose and maltodextrin are used as bulking agents, which is appealing to consumers. Aspartame and sucralose are hundreds of times sweeter than sucrose, so a serving size of these compounds alone would just be a few granules. We can see that the aspartame product has more calories than the sucralose product, but the difference is not as great as the difference between the pure aspartame and the pure sucralose compounds. With additional runs, the difference between the caloric content of these products could prove to be insignificant. Also notice the margin of error for the sucralose sweetener is slightly larger than the margin of error for the aspartame sweetener. This could be due to the fact that no energy corrections were considered for the chlorine atoms in the sucralose molecule. The PAR-BOM manufacturer does not suggest corrections for the combustion of chlorinated compounds. In the end, manufacturers can label these sweetener products as zero-calorie products because the FDA considers food serving sizes with fewer than 5 calories to be non-caloric. And indeed, at 3.80 calories and 3.1 calories for either product, that is fewer than 5 or less than 5, and so the companies can label these as non-caloric, as having no food calorie values. And here are my references. Thank you for taking the time to view this video, and I hope you found it informative. Thank you again.